Howdy, this is your friendly neighborhood physics teacher here, and we're going to talk about mechanical energy and open systems. If you haven't watched the closed system ones, please do, because I'm going to talk about what mechanical energy is in general over there. This one's just going to be basically what is considered an open system and doing practice problems or practice concepts with an open system. But if you have not gone back and if you haven't watched the closed system one, please watch that one first. Even if you're like, I understand closed, just do a little brief review and then you can come back to the open system. So open systems. An open system is where you have like the biggest difference between an open and closed system is, so if we're comparing open versus closed, okay? So open versus closed. An open system has conservative, I can't spell, conservative forces. So a closed system has conservative forces. So they both have conservative forces. The difference is an open system also has non-conservative forces. So refresher what a conservative force is. A conservative force is a force that constantly works on a system. So a conservative force would be like your spring force, your gravitational force. Those are all forces that are all kind of like in the system are always there. Non-conservative force would be like friction. So your open system has friction, your closed system does not. Your closed system energy is always conserved within the system. So basically, to put that into math terms, your mechanical energy initial equals your mechanical energy final, and anything and everything in between. It is always, your mechanical energy is constant. For an open system, that is not true. Your equation looks like your mechanical energy plus whatever work is being done to the system equals your mechanical energy after. Your mechanical energy is not conserved because of this work aspect of it. And it's always added because if it's a positive work, or if it's doing work to the system, it's adding energy, it'd be adding. If it's subtracting, then you have a negative force, so it'd be taking away. So your open equation always kind of looks like that. And so therefore your mechanical energy is not constant because of that work aspect. So let's do some practice problems. So we're going to mimic kind of like the ones we already did. It's just now we're going to add a non-conservative force in the mix. So the first one we did with it closed is we had a ball. Again, these are going to be conserved problems without numbers, so we can focus on the concepts. So we have a ball that has a mass and has a certain height, has a mass, has a height, but in this case, we are going to take air friction or air resistance in the mix. So it's a windy day. So how am I going to show? It's a windy day. Wind. So it's a windy day. So we're going to have some type of air friction. We're going to have some type of air friction. Now remember, air friction slows it down. So that's going to be a negative force. So we're still going to look at so this is still our mechanical energy before. This is down here where the ball, so it's falling. So where our ball is down here, we're still looking for the velocity. This would be down here, would be our mechanical energy final. But we have air friction we have to worry about. So that's when our mechanical energy initial plus the work equals our mechanical energy final, or after. So what type of energy is happening before you drop it? Hopefully you said gravitational. Now, as you're dropping it, your work starts playing a part in it. It's the work due to friction. And then that'll equal our mechanical energy at the end. So there's no height, so we don't have any gravitational, so it will be completely kinetic. Now looking at our work, we can sit there and expand, so it'd be mass times gravity times our height plus, in this case, it'd be a negative force times our distance is going to be the same thing as our height. So our y is the same thing as our distance, because that's where it fell. Our height and our distance are the exact same thing in this case. Equals our 1/2 mv squared. And then you would just solve to get v by itself. So there you go. So that's the big difference between the problem before and the problem after. Before, it was just your potential at the top equals your kinetic at the bottom, but adding air resistance in the mix, or air friction, they're not equal anymore. So example 2. So example 2, we had a spring. Spring with a mass on it. Oh, my equilibrium's a little off. Let's try that again. Okay. So this, again, is our equilibrium. So again, that means there's no elastic potential. There's no elastic potential when it's equilibrium. It's moving its fastest, so it's all kinetic energy. So again, remember, we have, I've sit there and I've pulled it. So I have my hand here. I'm sitting there holding it. From here to here is x, which is the same thing here. Just pretend I understand it's not. Can't. Not drawn to scale. And we do have some type of mass. And we have a spring constant. So this would, again, be our mechanical energy before. This would be our mechanical energy after. So final. Then we have our mechanical energy kind of in the, actually, we're just going to make this because it'll be the same. So our mechanical energy initial and our mechanical energy final. We're not going to worry about it being scrunched that way. So we're just going to look between these two. So it'll still be our mechanical energy plus work equals our mechanical energy final. Because it's on a table, so we have some type of friction. So again, we have some type of friction that's, so our frictional force, we have some type of friction. And friction slows it down, so it's a negative force. So as I pulled, I'm holding it. The type of energy that has is, again, just our, wrong color, our elastic potential. Plus whatever work's happening, this will be work done by friction again, equals, in the middle, we just have kinetic energy. We can expand that, so it'd be 1/2 kx squared, that should be a little k, plus would be a negative friction. And again, how much is moving is still k. So again, that x is still our distance it's moved. And that will equal our 1/2 mv squared. And again, you just manipulate to solve for v if we're looking for v. So there we go. So it looks very similar to our gravitational potential, just going sideways versus going up and down. Our third one is the fun, complicated one that involves everything. So let's give me a minute to set it up. So we have ground here. We have a ceiling here. Mass starting here. Mass here. Mass here. Mass here. Try and do the masses first, because I think I kept messing up on the springs. Spring. 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 Again, in the middle is our equilibrium. That's where our elastic potential is 0. We do have some type of height. So we have a initial height, and we have, again, we're just going to go here, so we have a final height. We still have an x, and then that'll be the same x there. We still have a mass. We still have a spring constant. This would be our initial mechanical energy, and this is our final mechanical energy. We have wind that's being blown. Hold on, that's gonna look like a spring. Hold on. So what would be a good wind? We'll do a light pink. So, ooh, look at the wind, look at the wind, look at the wind. So that would give us that we have some type of air friction. And remember, friction takes away. And don't forget, I've pulled it down. So I'm holding it here. Okay. So our mechanical energy, initial plus work equals mechanical energy final. So what type of energy is happening here? Again, it would be elastic because I'm holding it, I've stretched it, plus gravitational. This would be initial. Plus work equals, again, at the middle, would be our kinetic final plus our gravitational final, because it still has height. So if we're spreading that out, it'd be 1/2 mx squared plus mgy initial plus, that is still the force done by the friction, so it'd be our air friction, and the amount it's moving is, in this case, still x. Even though it has a height, but it's not moving all the way down, so it's just moving that x. So again, our x is the same thing as our distance. And that equals 1/2 mass v squared plus mass gravity and your final height. And from there you can solve for whatever you're looking for. So all these examples is when energy is being taken away. Can't really add energy to the system with system 1, but for these two we actually can. So we're going to look at 2b. So 2b, we're still doing the exact same example, but we're going to start with the first one. So it's here, and I'm literally pulling. So I am pulling. So we're doing a force applied here. So I'm pulling, I'm extending the spring. I'm extending the spring. So we're still going to have our initial mechanical energy plus work equals our final mechanical energy. But we're going to start from, this is going to be our, pick a different color. Pick a different color so it doesn't all blend together. Please erase. Why aren't you erasing? There we go. We'll do this color. Come on. So we have our initial plus work equals our final. So over here, this is going to be our initial, and this part is going to be our final for part 2. So at the beginning, there's actually no work being done because it's at equilibrium, it's chilling. So our mechanical energy is actually going to be 0. So the only way I'm putting work into it is I'm physically dragging it. So that would be our force applied times our x, because I've moved it x. And that will equal our elastic potential energy. Because right here, it just has elastic potential energy. So this would be work of the applied force. And if we're looking at this one, so again, I've extended, I'm pulling the force down. So this becomes our initial, and this becomes our final here. So this would be a 3b. So I'm adding work into the system. So it would be our initial plus work applied equal work after. So here we just have potential energy because it has height, but it doesn't have elastic because it's just at equilibrium. So we do have initial gravitational potential, plus it'd be again our force applied times that x equals, if I'm going here, we would have our elastic final plus our gravitational final. And again, you can expand it after that. So yeah, so that's what happens when it looks like you're adding energy to the system. So hopefully that helps. If you have any questions, please ask. Have a wonderful day. Bye.